What's up, internet? We're gonna do circuits. So I've got a lot of projects on the back burner that uh, all, all involve VCAs. So I thought it's a good time to do a deep dive on VCAs. So I'm gonna do that. One of the projects is this is our Cibrix distortion by Andromeda Corporation, and it's basically a standard clipping, hard clipping distortion, but it has some cool tricks in the clipping section. So I thought it would be interesting to make that into a Eurorack module with some CV control and maybe variations on the clipping selection. And then also this machine in the back is a new thing I just built, and I need a mixer for it. And I've got a lot of ideas for mixer stuff. But again, yeah, they all involve VCAs. So I'm gonna shut up about my future plans and let's get into the VCA deep dive. So out the gate, I have 3 big questions with a couple of sub questions. Firstly, which style of VCA is the cleanest, like least distortion? And when we say distortion in VCA world, we're not talking about fuzzy guitar distortion. We're talking about, is it accurate to the inputted waveform? So which style is the cleanest? There's a lot of different ICs that people use. Like the OTAs, operational transconductance amplifiers, versus doing discrete parts. And there's a bunch of different types of OTAs. And then there are like chips that have most of the VCA on the chip itself. And yeah, I want to find out which one of those is the cleanest. Which op amp has the best balance of being clean, because you also need an op amp for most of these circuits. So which op amp is the cleanest, as well as the most practical, because I suspect there are probably some very, very high-end op amps out there that have the best stats, but are silly expensive for what they do, relatively, I imagine. I don't really know. I mostly deal in the cheap ones, the TL07Xs. Those are great. They work great. I might just end up using those, but we're gonna do some research. Another thing to consider is that I was given a bunch of parts, and I have a bunch of these LM 13700s, and these are a bunch of 3080s, which I think have pretty crummy stats, but maybe I could make some cool vintage circuits with that. I think some classic pedal compressors use these. So I don't know, if you know of a cool circuit that uses the CA 3080, leave a comment. Maybe we can build some clones together. And then a lot of these guys, if you're using the OTA style VCA, they need voltage to current converters. And there's a lot of variations in that stuff. And I have done some research on those, but it's still, I don't really understand it intuitively yet. I could do all the math and stuff, but I don't quite get it. So I'm hoping if I just read about that stuff again, I'll get it intuitively. Yeah, and then the other thing is that when looking at all those circuits, I have a bunch of examples of them. Some of them are linear, some of them are exponential curves, but I'd love to have linear to exponential be like a smooth on a knob. Like if you're familiar with maths, the Eurorack module, it's got a very nice knob that'll do that, where if it's set there, it's linear. If it's set over here, it's logarithmic. And if you set the knob all the way over that way, it's exponential. It's a very useful knob. It's great. So it'd be great to have that to know how to do that with a current to voltage, or voltage to current converter. Yeah, so I thought I'd start out by asking, GPT. That's not normally what I do, but I think AI stuff's pretty interesting, and I'd like to be using it as it develops. I don't want to get left behind. So let's start there. All right, so I forgot to mention 2 things earlier. First, and secondly, I made a post on Reddit earlier in the week asking the synth DIY community about these same questions. I got some really great responses, and to sort of average out that, and then what I just got from ChatGPT. I'm using GPT-3, by the way. I didn't pay for the newer version. I'm just checked the free version. And it did have a couple of weird hallucinations. It told me the 3340 was a VCA, and that's a VCO. But it did mostly agree with the Reddit thing that the SSM 1264 seems to be the most popular one. People really like that. They say it has good stats. 4MS uses it for their VCA matrix, and then I think their quad VCA mixer, which is like super popular. Everybody loves that one. Mutable Instruments Veils, also super popular. Mike Irwin, not super popular, but very cool. They know what's up. AI Synthesis, which is whatever. QPass by Make Noise uses it. I don't know, that's maybe not, you probably can't find that information on the internet, but I just pulled mine apart and looked at it, and they do use one. It's a 2021-64 in there for the quad peak animation system, the QPass by Make Noise. And, I think Tony Rolando is just one of the coolest circuit guys out there. So if it's good enough for him, it's probably good enough for me. And then also Electrosmith uses them, which I don't know if that means that it has the best stats, but it does mean that it's popular, They make great stuff, but I think they're targeting what's going to sell, what's popular, you know what I mean? So I'm going to check the stats on that one. That's all I mean. Yeah. Oh, and then the other one that people seem to really like that I was surprised at was the Surge VCA, which isn't for Eurorack. That's a different standard if you don't know what Surge is. But I checked out the schematic, and it's basically a differential pair, BG. Here's the Surge VCA. I didn't look at this that closely earlier. I thought this differential pair here was for the audio, but that's just for the CV. This is an OTA. I didn't look closely enough. I just figured that was just some audio amp. But yeah, that's the 3080, which I mentioned earlier. I have like 10 of those. So I don't know, maybe I'll build one of these. But I think probably for my own designs, if I'm trying to build a general purpose VCA, for mixers and distortion circuits and CV control later and all that stuff, I'll probably look for something else, because the 3080 is obsolete, and this differential pair is probably finicky to get right. So I'm sure this is a great circuit, but probably just too much hassle for my purposes. Yeah, so I got my short list. I didn't list them all. I don't want to bore you to tears. I'm just trying to bore you a little bit. So I got my short list. I'm going to check the stats now. I got the popular opinion. Let's see the facts, All right, so I thought this would be a good thing to share with everybody. This is ChatGPT's answer to the question about what stats are most important when comparing ICs for this application. So for mixer circuits, I asked it for mixer and VCA, right? So for mixer circuits, obviously gain voltage, duh. It says, a gain of 1 is equal to unity, but I think I'll actually try to get more gain than that so that you can bring line level signals into the thing. Maybe on a switch or something, there'll be like a pad. I don't know, but whatever. Voltage gain, duh. Total harmonic distortion. That's a really important one, obviously. Noise figure equivalent input noise, ein. Common mode rejection ratio. Now, I'm familiar with this in relation to, what do you call it? With a pair of transistors, the differential pair. And I believe that OTAs are basically differential pairs with a bunch of extra stuff around them. So that may be exactly the same thing. But we'll look into that, because I don't really know about any of these chips, how their common mode rejection ratio is, or even why that's super important, honestly. Number of inputs and outputs, whatever. That's an easy one to change. For VCA circuits, input offset voltage, gain range. That one kind of sounds like I probably won't matter, if I'm being honest. I bet all of them can at least make it to unity gain, and then extra gain is just bonus stuff, really. Although I intend to use it, so it's not that bonusy. Total harmonic distortion. This seems to be the most crucial thing. It's just based on what everybody says on the internet. And again, we'll get into the actual numbers of these, but I'm just trying to prioritize what numbers to pay attention to. So I think number 3 is actually number 1 here for my purposes. Control voltage range. That's a thing that can be easily adapted. You can easily cut that down or amplify it up depending on what the chip wants, so I'm not worried about that. Dynamic range. Obviously, this is important, I guess, but I don't really understand. The maximum and minimum levels the VCA can handle. You think that's the input voltage? We'll ask GPT. What is that? That's a lot. Oh, we got math? I wonder if that's accurate. GPT-3 currently, I don't know, you might be watching this in the future. Currently, GPT-3 is infamous for screwing math up. So, the dynamic range of electronic circuit is a measure of the ratio between the maximum and minimum levels of signal that the circuit can handle without distortion or degradation. Okay, so I think I understand this. In, what do you call them? Operational transconductance amplifiers, the inputted signal has to be actually really, really small. It has to be in the microvolts. I think it's 20 microvolts for most of them, somewhere around there. Really small. Or millivolts, sorry, not microvolts. That's millivolts, 20 millivolts. So that's probably what this is all about. But that's another thing that's super easy. You put in 10 volts to peak, and you just put an attenuator before the input of the thing. So that I don't think we got to worry about that. In the context of VCA, the dynamic range is crucial because it defines the extent to which the on distortion or noise. Decibels as calculated as, okay, whatever. Maximum output voltage is the highest level of output signal it can produce without distortion. Okay, so we should pay attention to that. Yeah, so we'll just make sure to double check that before we commit to an IC, but I don't think that we have to worry about that too much either. Back to the list, dynamic range, blah, 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 voltage controlled response characteristics. Now this one's gonna be important for sure. Check the linearity and response characteristics of the signal to noise ratio. Definitely important. We want it to be super clean, especially if we're going to use this for mixers. Supply voltage range, that's another one. That's kind of whatever, easy to fix. So, okay, so here we go. We got, was that 5 things to focus on? All right, I'll pull up some data sheets and we'll do some comparisons, baby. Woo! Data sheets. Yes. So this was interesting. I just tried to get ChatGPT to compare the total harmonic distortion figures on the data sheets of these ICs that I'm interested in, but it refuses. I've tried multiple times here because that is real-time data. So it just won't read off of data sheets. So I just asked Bing the same question to compare total harmonic distortion on the data sheets of all these chips, and it gave me a similar reply at first, saying it couldn't access or read PDFs or external websites that are contemporary or whatever, but then it actually went and gave me an answer to the question, so that's nice. And on top of that, we got little links here. So like, I mean, well, first of all, there is a harmonic distortion figure on the data sheets for these last 2, but it says that it couldn't find it, but that information does exist. I just looked at it. But for what it did find, look at this. It's like you can click on it and it'll cite its source. Isn't that nice? And this is the right one. I have this open over, I was looking at it earlier. Look at that. Good job. Thanks, Bing. Good job, Microsoft. Okay, here come the stats. I'm going to do it as a still image, so hit pause if you want to read this for whatever reason. So after much AI-assisted data sheet, mining, I've compared all of these guys with all these different stats and stuff, and it seems to me that the total harmonic distortion is actually pretty much representative of my impression of these chips. I think the THAT 2181 is our best option, and if that is too expensive, we can check out the 2180 because it's just like a slightly less nice version of that. And then if that's not great either, our number 3 choice will be the SSM 2164. Because these two down here had either kind of middling or bad, not bad, but kind of middling stats, or there just wasn't information. Like the AS3381 has a really crummy data sheet. There's very little information on it. But that's where we're at. THAT chips, and then maybe the SSM if those are cost prohibitive or annoying for some other reason. Yeah. All right, so I hope that wasn't too boring. We're going to get into more exciting stuff in the next vlog, I'm going to call it. Have a nice day. Like and subscribe. Circuits!